Welcome to AI Paper Podcasts. Today we're looking at a really interesting one, Skywork R1V, pioneering multimodal reasoning with chain of thought. This comes from the folks at Skywork AI, Kunlun Inc.
Yeah, and the headline here is pretty striking. We're talking about a 38 billion parameter model.
Yeah.
Which sounds big, but in the grand scheme of things these days.
Right, compared to the giants, it's relatively lean.
Exactly. And yet it's achieving multimodal reasoning performance that's seriously competitive with much, much larger models. That's the really exciting part.
So our mission today is to kind of unpack how they pulled this off. We'll dig into their approach to multimodal transfer, the training strategies they used, and this clever way they generate reasoning data.
Absolutely. If you're trying to figure out how to get that high-end reasoning capability without needing, 100 billion plus parameter model, this paper offers some really valuable insights.
Okay, so maybe let's start with that quick summary for folks who might need the short version for, say, a quick update.
Sure thing. So in a nutshell, Skywork R1V is this 38B parameter multimodal model. Its strength lies in reasoning.
And the key is how it gets there.
Precisely. It efficiently transfers reasoning abilities from large language models over to visual tasks. And it does this using a surprisingly lightweight visual projector.
Okay.
Then there's the training. They use a hybrid approach mixing supervised fine-tuning, SFT, with something called Group Relative Policy Optimization, or GRPO. This helps align the visual and text understanding better.
In the data.
They generate reasoning data using what they call adaptive length chain of thought distillation, basically making the reasoning steps just as long as they need to be, which is efficient.
How does it perform?
Really well on key benchmarks. It hits 69.0 on MMMU, 67.5 on MathVista. Those are tough multimodal tests. And it still holds strong on text reasoning. 72.0 on MA, 94.0 on Math 500.
Wow, okay.
And maybe the best part for the community, they've open sourced all the model weights.
That's huge. Okay, great summary. Let's dive into the details then, starting with this efficient multimodal transfer. We know LLMs are great at text reasoning, but getting that same power for multimodal tasks.
Yeah, that's the bottleneck. The paper points out, and it's widely known, that extending that deep logical reasoning, think about like understanding geometric proofs from a diagram or complex scientific problem solving involving visuals, it's a real challenge.
What makes it so hard?
Well, it's fundamentally about aligning the visual understanding, usually from a vision backbone model, with the language model in a way that supports complex inference. It's not just recognizing a cat, it's understanding the relationship between visual elements and textual descriptions for logical steps.
And current vision language models, or VLMs, often fall short there.
They do, especially on that really deep, intricate reasoning. Plus, getting the right kind of training data specifically designed for multimodal reasoning, is difficult.
So Skywork R1V's big idea is don't reinvent the wheel.
Sort of, yeah. They take their existing R1-series language models, which are already good at reasoning, and find an efficient way to port that reasoning capability over to the visual side.
And the key piece of tech for that is this lightweight MLP projector.
Exactly, a multi-layer perceptron. It acts as the bridge. And the really clever insight, I think, is that they decouple the problem.
Decouple how?
Instead of trying to teach a model vision-language alignment and complex reasoning all at once, they separate it. First, build a really good, efficient translator between vision and language, that's the MLP. Then plug that translator into a language model that's already a powerful reasoner.
Okay, that makes intuitive sense. Saves you needing tons of specialized multimodal reasoning data from the get-go.
So how does this transfer work in practice? They mentioned 3 steps.
Right. Step 1 is MLP Initialization. Here, they take a standard vision encoder, a vision transformer, or VIT, and they need to connect it to a language model. But interestingly, they don't initially connect it to their final super reasoning LLM.
Oh, which one do they use? They use a substitute LLM, First Quen 2.532B Instruct. It shares the architecture with their target reasoning model, but maybe doesn't have all the reasoning fine-tuning yet. The MLP adapter is trained to connect the VIT to this substitute model.
And that training is the SFT, the supervised fine-tuning.
Correct. And it's quite methodical. They do an initial broad tuning on about 2 million samples. Then they refine it on a smaller, high-quality set of 200K samples, quality checked by GPT-4, actually.
Okay.
And finally, a last tuning stage on about 40,000 really high-quality chain-of-thought examples. They give all the hyperparameters too: context length 16K, weed decay 0.05, warm-up 3%, batch size 512, 1 epoch per stage.
Right, lots of detail there for replication. So this first phase gets the MLP understanding how to translate vision into the language space of that substitute model.
Exactly. It establishes that basic visual linguistic mapping.
Okay, then step 2, model reassembly. This sounds like where the magic happens.
It really is quite elegant. They take that MLP adapter they just trained.
The one trained with the substitute LLM.
Yes. And they unplug it from the substitute model and plug it into their actual target reasoning model, the DeepSeek R1 Distill Qwen 2.532B. They use the same VIT encoder, but now the MLP connects the VIT to the powerful reasoning LLM.
And they switch the tokenizer to match the reasoning LLM as well. What happens then? Do they have to retrain everything?
Well, here's the kicker. The paper notes that even without any further fine-tuning at this stage, just by assembling these pre-trained parts, the model already shows significant performance.
Wow, so that MLP learned a pretty general visual to language mapping.
It seems so. It suggests the mapping wasn't overly specific to the substitute LM, but captured a more fundamental translation that still works pretty well when connected to a different, though architecturally similar, model. It's quite robust.
Very cool. Okay, and the final step, step 3, is modality alignment.
Right. Now they have the final architecture assembled, VIT MLP Reasoning LLM. The goal here is to fine-tune the connection, specifically that MLP bridge.
But
Crucially, they freeze the weights of the VIT and the big reasoning LLM. They only train the parameters of the lightweight MLP adapter.
so they're refining the translation layer without messing with the core visual understanding or the core reasoning engine.
Exactly. This preserves those hard-won reasoning capabilities of the LLM while making the visual input speak its language more fluently. And this fine-tuning uses their hybrid optimization framework and the adaptive cockpit data we'll get to.
Okay, perfect segue. Let's talk about that hybrid optimization framework. Figure 1 in the paper maps it out. It looks like a mix of SFT and GRPO.
Yeah, group relative policy optimization. It's a multi-stage process designed to really hone the model's multimodal reasoning. Stage 1 is pretty straightforward, initial training.
This is just a standard SFT on the whole assembled model, right? Using all their multimodal data.
Correct. This gives them their baseline multimodal model, which they call M0.
Then stage 2 gets more complex. Iterative training with customized data.
Yes, this is where things get iterative. They train a sequence of models, M1, M2, M3, M4. And for each step, say going from MT1 to MT, the training data is specially selected.
Customized how? They mentioned DRAMM and ET1.
Right, so DTD, the dataset for training model MT, is made of 2 parts. First, DROB. This is a refined dataset. They use a reward model. Think of it as an automated judge to score all their data samples from 0 to 5 on quality.
Okay.
For each iteration T from 1 to 4, they raise the quality threshold. Start with 2, 2, then 3, then 4, then 5. So DROB only includes samples scoring above that threshold. They're progressively focusing on higher and higher quality data.
Smart, like focusing your studying on the best material. What about the other part, E1?
E for error. E1 contains the samples that the previous model MT1 got wrong.
So forcing the model to revisit its mistakes.
Exactly. It specifically targets the model's weaknesses, the challenging cases it failed on before. So each iteration fine-tunes on a mix of high-quality examples and the tricky ones it needs to learn from.
And they do this 4 times, 1 epoch each iteration, combining DRAM and EAT1. They tweak the learning rate a bit after the first round, but other params stay mostly the same.
Yep, it's a cycle. Train, identify high-quality examples, identify errors, combine them, train again, refine, refine, refine.
Okay, that covers the iterative SFT. What's the final stage? Stage 3, reinforcement learning.
Yes, using GRPO. This seems to build on their previous work with the text-only DeepSeek R1 model. They use reinforcement learning to further polish the model's output.
What kind of reward signal do they use?
It's rule-based. It looks at both the accuracy of the answer and whether it follows the correct output format. They apply this GRPO only to the very highest quality data subset, the one selected with the top threshold of 5 by the reward model.
And they provide the GRPO hyperparameters. Learning rate 1E6, temperature 1.0, generation number 8, max output 8K tokens.
Right. The goal here is better generalization and, interestingly, better reasoning rationality. They mentioned they don't just pick the final GRPO checkpoint. They evaluate recent checkpoints and choose the one that best balances raw performance on benchmarks with the sort of coherence and logical soundness of the reasoning steps it generates.
Fascinating. Okay, so we have the efficient transfer of the hybrid training, but the quality of that training data is obviously crucial. Let's talk about the adaptive length chain of thought distillation. Figure 2 helps visualize this.
This is another really neat part. The core problem they're tackling is that sometimes, for simple questions, models generate these really long, unnecessary reasoning chains over thinking. But for complex questions, you need detailed reasoning.
So they want the reasoning length to adapt.
Precisely. They want it dynamic. It starts with a quality and difficulty assessment module, or QDAM.
Okay, what does QDAM do?
It uses GPT-4o mostly to score image-text pairs. It calculates a vision score and a text score.
What goes into the vision score?
Two things. Image clarity, which they check automatically using things like blur detection and image necessity. Does the image actually contain info needed to answer the question? GPT-4o helps assess necessity.
And the text score?
That looks at question quality, is it clear? Difficulty level, what knowledge is needed? And reasoning demand, how many steps seem necessary? GPT-4o handles all of these text assessments.
So QDAM gives a rich profile at each data point. What's next?
Next is the Vision Text Integration Analyzer, VTIA, also using GPT-4o. Its job is to figure out how tightly coupled the image and text are for the specific query. It generates an integration score, SI.
An integration score, meaning?
Meaning, how deeply do you need to combine information from both the image and the text to get the answer? High SI means they're very interdependent, like interpreting a complex scientific diagram with dense captions.
And low SI?
Low SI would be for things like simple object recognition, where the text just asks, "What is this?" and the image shows it clearly. The paper gives examples of linguistic patterns associated with high integration, like causal words, because, therefore, or references requiring spatial reasoning within the image.
Got it. So you have quality scores, difficulty scores, and this integration score. How do they use them?
They feed into the Dynamic Reasoning Length Controller, or DRLC. This model uses those scores to adjust the repetition penalty used when generating the reasoning chain data.
The repetition penalty. A lower penalty usually means longer, more varied output, right?
Exactly. The formula is a bit complex, but essentially, if the scores, vision, text integration are high, indicating a difficult, high-quality, highly integrated problem, the DRLC lowers the repetition penalty.
Letting the model generate a longer, more detailed chain of thought.
Right. And if the scores are low, simple question, clear image, low integration, it increases the penalty, encouraging a more concise reasoning process. They have hyperparameters I'd add to await the different scores.
That's really clever. It guides the model to show its work appropriately. So how is the actual data generated then?
Through a multi-stage self-distillation pipeline. First, the model itself generates answers, including explicit reasoning steps marked by special think tokens. The DRLC controls how long these think sections tend to be via that repetition penalty adjustment.
Okay, the model generates a potential answer with reasoning. Then what?
Then, GPT-4o acts as the teacher. It checks if the final answer is correct. If it is correct, they keep the model's generated reasoning chain as is.
And if it's wrong?
If it's wrong, GPT-4o doesn't just discard it. It analyzes the mistake and actually revises the reasoning chain to make it logically sound and lead to the correct answer.
So it's like guided practice. The model tries and gets corrected when needed. When does this happen?
This whole distillation process runs before the initial Stage 1 SFT, and then it's repeated before each iteration of the Stage 2 iterative SFT. So the training data itself keeps getting refined alongside the model.
Wow, okay, that's a sophisticated data generation loop. No wonder the results are good. Let's talk about those results. Where did they test this model?
They used a pretty challenging suite of benchmarks. For core reasoning, they used Math 500, AIME 2024, which is notoriously hard, high school math, and GPQA for general knowledge.
And for the multimodal part?
MathVista, focusing on math reasoning and visual context, and MMMU, which is a big benchmark with college-level questions across lots of different subjects, all multiple choice but requiring multimodal understanding.
How did they run the evals?
Max generation length was 64K tokens. They use specific prompt formats for different tasks, following standards where available. The main metric is pass at 1, getting it right on the first try, average over 5 runs for stability.
Okay, so let's look at Table 1, comparing it to similar sized models. How did Skywork R1V do?
Exceptionally well. On Math 500, it got 94.0. On AIME 2024, 72.0, significantly ahead of others in that size class listed.
And on the visual side, MathVista and MMMU.
Still very strong. 67.5 on MathVista, which is competitive even with larger models. And on MMMU, a score of 69.0, which beat out several larger models listed there, like Intern VL2 40B and even the 72B Quen VL2 model.
That really shows the power of their approach, working well across both text and multimodal reasoning. What about figure 3, comparing it to the big players?
Yeah, that's maybe even more impressive. Despite being only 38B parameters, it's holding its own against giants like Claude 3.5 Sonnet, and even matches GPT-4o on MMU 69.0. It also edges out Claude 3.5 Sonnet on MathVista.
That efficiency is remarkable. Seeing a 38B model compete at that level.
Wow. The paper also shows some specific examples, right? Figures 4 and 5?
Yes, qualitative examples. Figure 4 is a geometry problem about a pentagon. It shows the model breaking it down step by step, using geometric rules to set up an algebraic equation, solving for x, and then calculating the final angle.
Demonstrating that integration of different reasoning types. Exactly. And figure 5 is a chart analysis task life expectancy trends. The model interprets the graph, identifies trends, calculates the gender gap over years. Importantly, it shows self-correction in its reasoning path and correctly finds the year with the largest gap.
That self-correction is a good sign of robust reasoning. It's not just pattern matching. Okay, and finally, Table 2 breaks down performance at different training stages.
Right, looking just at the MMMU benchmark, the model after just the initial MLP initialization, step 1 of transfer, already scored 64.0, which is pretty good on its own.
And after just assembling the parts, step 2, before the main fine-tuning,
it scored 60.2. Still impressive, beating smaller models and nearing larger ones just by plugging the pre-trained MLP into the reasoning LLM.
Then the iterative SFT, stage 2 of optimization, brought consistent improvements.
Yeah, it climbed steadily from that 60.2 up to 65.6 across the 4 iterations. Shows that refinement process was working well.
And the final RL stage, the GRPO.
That provided the last big jump, pushing the MMMU score up to the final 69.0. They also mentioned qualitatively that this RL stage seemed to make the model produce longer, more detailed reasoning steps, perhaps learning to articulate its thoughts better.
Okay, so let's try and wrap this up. The key takeaways seem to be this really efficient multimodal transfer using that lightweight MLP.
Right, decoupling alignment from reasoning preservation.
Combined with that sophisticated hybrid optimization framework, mixing iterative SFT with GRPO.
Focusing on high-quality data and error correction.
And fueled by this very clever adaptive length chain of thought distillation method for generating just the right amount of reasoning for the training data.
Exactly. And all those pieces together allow this 38B parameter model to punch way above its weight, delivering reasoning performance on par with models several times larger, both open and proprietary ones.
It's a really significant result for making powerful multimodal AI more efficient and accessible.
Absolutely, and the fact they open source the weights is fantastic for the research community. It allows everyone to build on this, experiment, and push things further.
It really helps democratize access to these advanced capabilities.
Definitely. So maybe a final thought for everyone listening, especially if you're working in AI or ML, seeing this level of efficient multimodal reasoning, what does it make you think about? What kinds of real-world problems that need understanding of both images and text, suddenly seem more tractable? What new applications could this unlock in your field?
That's a great question to ponder. Definitely food for thought.